Welcome to our first video on chapter 2, and we are going to be talking about matrices and systems of linear equations. So if you recall, when we were trying to find the points of intersection of a line and a plane, or when we had two planes, we want to find the points of intersection, we would end up with some simultaneous equations, and we would then solve them to find the point of intersection. So now we're going to focus on systems of equations and find ways of solving them in when we are in R3, R4, R5, and even Rn, where n is a very large number. So this is the focus of this chapter, and then we are also going to then see how we can do that using matrices, because matrices have a lot of properties that we can use. So in this video lecture for chapter 2.1, we are going to focus on systems of equations. So let's start off with a definition. What is a system of equations? A system of equations is a collection of two or more equations in one or more unknown quantities, x1, x2 up to xn. And a solution of a system of equations in the unknown quantities x1, x2 up to xn are values x1 equals to a1, x2 equals to a2, up to xn equals to an, for the unknowns that simultaneously satisfy all the equations in the system. So in other words, if we replace x1 with a1, x2 with a2, and xn with an in the system of equations, if the left hand side is equal to the right hand side for every equation, then we call those values a1 up to an a solution of the system, right? And we typically write these kind of solutions of a system of equations in a vector form. So we write it as a vector a1 up to an, and note that this vector is a solution to the system of equations, right? It's just one solution, right? And then so we have a system of equations can have a unique solution, or might not even have a solution, or might have more than one solution, right? And we're going to see a few examples to illustrate this. So let's start off with our first example, and that's example 2.1.1, and it says solve the system of equations, and the system of equations has 3x plus 5y is equal to 24, x plus y is equal to 6, and give a geometric interpretation for the solution. Now, so for us to solve this, we'll first multiply the second equation by 3, and if we do that, we obtain that we have 3x plus 3y is equal to 18, right? And now we have a new system with 3x plus 5y is equal to 24, and 3x plus 3y is equal to 18. Now, the second step, if we replace equation 1 with equation 1 minus equation 2, so in other words, we are saying 3x minus 3x, we get a 0, 5y minus 3y, we get 2y, and then 24 minus 18, we get 6. And now we have a new system with 2y minus 6, sorry, 2y is equal to 6, and then 3x plus 3y is equal to 18. And from the first equation, we can see that if we divide both sides by 2, we get y is equal to 3. And then if we substitute that y is equal to 3 into the original equation, or the second equation here, we see that y is also equal to 3, right? So thus we can conclude that there is exactly one solution, and the solution is xy is equal to the vector 3, 3, right? And so if we think of it geometrically, we'll see that if you look at these two equations in our system, the first equation represents a line, the second equation also represents a line. So so the first equation will be that one, and then the red one, it will be the second equation. And we see that these two equations meet at this point, and that is the point 3, 3, and this tells us that this will be the solution to our equation. Why? Because it is the point where these two lines meet. So therefore, in other words, that point is where the two equations are satisfied simultaneously. So therefore, the geometric sense of the solution 3, 3 agrees with our algebraic sense, where we calculated and we found out that there's exactly one solution, 3, 3, and that agrees with our drawing here, right? Let's go on to another different type of equation, or a different equation that will give us a different type of solution, let's say that, right? So this is example 2.1.2 in the textbook, and it's the same. Solve the system of equations 2x plus 3y is equal to 7 and 4x plus 6y is equal to 8, and give a geometric interpretation for the solution. So if we multiply the first equation by 2, we'll see that we have 4x plus 6y is equal to 14, and now we have a new system with 4x plus 6y is equal to 14 as equation 1, and 4x plus 6y is equal to 8 as equation 2. Now if we replace equation 1 with 1 minus 2, we will see that 4x minus x is equal to 0, 6y minus 6y is equal to 0, and then 14 minus 8 is equal to 6. So we have a new system, 0 is equal to 6, and 4x plus 6y is equal to 8, right? And from here we can see that 0 is equal to 6 is impossible. So what does that tell us? That actually tells us that the two equations that we originally had, cannot be satisfied simultaneously, and because if it would happen, then it would mean that 0 will be equal to 6, which we know is impossible. So we can conclude that the system has no solution, right? And let's think about it from a geometric point of view. So we've got these two equations, and we can see that these two equations represent two lines, right? So if we draw the two lines, you'll see that the two lines will be parallel, and because they are parallel, they are not going to intersect at any point, right? So if that's the case, what it means is we can't find a point of intersection, meaning that we can't find a solution for the system, right? So we can't find a point which is on the two lines because they are parallel, so therefore we can't find a solution, as we concluded when we were looking at when we did the algebraic calculations. So, and this actually agrees with something that we have already established in theorem 1.4.19, which states that distinct parallel lines do not intersect. So therefore, this agrees with what we already have. Right, let's look at a third example. So this is example 2.1.3 in the textbook, and it says solve the system of equations. And the system of equations consists of 2x minus 5y is equal to 7 and 6x minus 15y is equal to 21, and give a geometric interpretation for the solution. Right, so if we multiply the first equation by 3, we are going to see that we will have 6x minus 15y is equal to 21 as equation 1, and then the second equation would be 6x minus 15 is equal to 21. So if you look at it, you'll see that we basically have one equation, right? So, and we have got two unknowns. So what it means is, if we choose a value for x, and let's call it a, where a is a real number, then we are going to find a corresponding y, which if you make y the subject of the formula, you find out that y is equal to 2 over 5a minus 7 over 5, so that the pair is a solution of the system. So for any real number that you pick, you always find a corresponding y. For any real number a that you pick, you always find a corresponding y. So let's say if we pick x is equal to 0, we find a value for y. X is equal to 1, we find another different value for y. So therefore, we are going to have an infinite number of solutions for this system. And the infinite number of solutions can be written in this form. xy is the vector t, 2 over 5t minus 7 over 5 for some real number t. So because t is arbitrary, we know that we are going to have an infinite number of solutions. We're supposed to have a bracket here, right? Okay, so let's think about it from a geometric point of view. So if you draw the two lines, you'll see that it's basically one line that we have. And so any point that you pick on this line is going to satisfy both equations, because both equations or both lines are just the same line, right? So any point that you pick is going to satisfy the two equations, and that means that any point that you pick is a solution to the system that we have. And that means that we have, because this line is a set, it's an infinite set, that means we will have infinitely many solutions, right? So the geometric sense tells us that we have got an infinite number of solutions, because every point on the line is going to satisfy the two equations. And the algebraic calculations showed us that we have got an infinite number of solutions. So they both agree on this, right? So we had three scenarios: one where we had one solution, the other was where we had no solution, and the last one we had infinitely many solutions. And this is actually a result for systems of linear equations. We haven't defined what linear equations are. We'll look at that in the following sections. But the three that we have looked at so far are systems of linear equations, and we have seen that either you have one solution, or you have no solution, or you have infinitely many solutions. This is actually a theorem for systems of linear equations, that these are the only options that you have for a system, right? So go and look at examples 2.1.4 up to 2.1.6, where the systems are in higher dimensions. So, the way the systems, you have more unknowns than 3. So you've got maybe, more than 2. Sorry, not more than 3, more than 2. So you might have 2 or 3 unknowns. You might have 3 or 4 unknowns in these examples. So go and look at them, and then for a system that is not linear, and we haven't defined linear, but example 2.1.8 is a system of nonlinear equations, right? And we are going to see that we might have a different number of solutions, right? From the one solution, no solution, or infinitely many solutions. And so example 2.1.8 says, solve the system of equations x plus y is equal to minus 3, and then x squared plus y squared is equal to 17, and give a geometric interpretation for the solution, right? So if we think about the first equation, we can make y the subject of the formula and find that y can be written as, the first equation can be written as y is equal to minus 3 minus x. And if we substitute that into the second equation, so where there is a y, here we put minus 3 minus x, we find out that we are going to have x squared plus minus 3 minus x squared is equal to 17. And if we expand and then simplify and factorize, we find out that we have x plus 4, x minus 1 is equal to 0. So what it means is x is either equal to minus 4 or x is equal to 1, right? So when x is equal to minus 4, y is equal to 1. And when x is equal to 1, y is equal to minus 4. Therefore, the system has two solutions. And if we write them in vector form, it's xy is equal to minus 4, 1, or xy is equal to 1, minus 4, right? Now let's look at it from a geometric point of view. Right, so if you look at the two equations that we have, the first one is a line, right? And then the second one, if you look at it closely, you'll see that that is just a circle with center the origin and radius root of 17. So if we draw the two curves, we see that we've got a line and then we've got a circle, and then these two intersect at this point and then at that point, right? And these are the points that we found to be minus 4, 1 and 1 minus 4. So that one is 1 minus 4, and then that one is minus 4, 1. And these are the points of intersection, so therefore these are the solutions to the system of equations. So the geometric sense agrees with our algebraic calculations. So go and look at example 2.1.9 in the textbook. It is another system of nonlinear equations, and it's going to have 4 solutions. So go and explore it there. Thank you. That is all for the first lecture.